A unit of measurement is a definite magnitude of a physical quantity, defined and adopted by convention or by law, that is used as a standard for measurement of the same physical quantity. Any other value of the physical quantity can be expressed as a simple multiple of the unit of measurement. For example, length is a physical quantity. The meter is a unit of length that represents a definite predetermined length. When we say 10 meters, we actually mean 10 times the definite predetermined length called meter. The definition, agreement, and practical use of units of measurement have played a crucial role in human endeavor from early ages up to this day. Different systems of units used to be very common. Now there is a global standard, the International System of Units, the modern form of the metric system. In trade, weights and measures is often a subject of governmental regulation, to ensure fairness and transparency. The International Bureau of Weights and Measures is tasked with ensuring worldwide uniformity of measurements and their traceability to the International System of Units. Metrology is the science for developing nationally and internationally accepted units of weights and measures. In physics and metrology, units are standards for measurement of physical quantities that need clear definitions to be useful. Reproducibility of experimental results is central to the scientific method. A standard system of units facilitates this. Scientific systems of units are a refinement of the concept of weight and measures developed long ago for commercial purposes. Science, medicine, and engineering often use larger and smaller units of measurement than those used in everyday life and indicate them more precisely. The judicious selection of the units of measurement can aid researchers in problem solving. In the social sciences, there are no standard units of measurement, and the theory and practice of measurement is studied in psychometrics and the theory of conjoint measurement. History. A unit of measurement is a standardized quantity of a physical property, used as a factor to express occurring quantities of that property. Units of measurement were among the earliest tools invented by humans. Primitive societies needed rudimentary measures for many tasks. Constructing dwellings of an appropriate size and shape, fashioning clothing, or bartering food or raw materials. The earliest known uniform systems of weights and measures seem to have all been created sometime in the 4th and 3rd millennia BC among the ancient peoples of Mesopotamia, Egypt and the Indus Valley, and perhaps also Elam in Persia as well. Weights and measures are mentioned in the Bible. It is a commandment to be honest and have fair measures. In the Magna Carta of 1215 with the seal of King John, put before him by the barons of England, King John agreed in clause 35, "There shall be one measure of wine throughout our whole realm, and one measure of ale and one measure of corn, namely, the London quart, and one width of dyed and russet and hauberk cloths, namely, 2 ells below the selvage." Systems of units. Traditional systems. Historically, many of the systems of measurement which had been in use were to some extent based on the dimensions of the human body. As a result, units of measure could vary not only from location to location, but from person to person. Metric systems. A number of metric systems of units have evolved since the adoption of the original metric system in France in 1791. The current international standard metric system is the International System of Units. An important feature of modern systems is standardization. Each unit has a universally recognized size. Both the imperial units and U.S. customary units derive from earlier English units. Imperial units were mostly used in the British Commonwealth and the former British Empire. U.S. customary units are still the main system of measurement used in the United States, despite Congress having legally authorized metric measure on 28 July 1866. Some steps towards U.S. metrication have been made, particularly the redefinition of basic U.S. and imperial units to derive exactly from SI units. Since the International Yard and Pound Agreement of 1959, the U.S. and imperial inch is now defined as exactly 0.0254 meters, and the U.S. and imperial avoirdupois pound is now defined as exactly 453.592337 grams. Natural systems. While the above systems of units are based on arbitrary unit values, formalized as standards, some unit values occur naturally in science. Systems of units based on these are called natural units. Similar to natural units, atomic units are a convenient system of units of measurement used in atomic physics. Also, a great number of unusual and non-standard units may be encountered. These may include the solar mass and the megaton. Legal control of weight and measures to reduce the incidence of retail fraud. Many national statutes have standard definitions of weight and measures that may be used, and these are verified by legal offices. Base and derived units. Different systems of units are based on different choices of a set of base units. The most widely used system of units is the International System of Units, or SI. There are 7 SI base units. All other SI units can be derived from these base units. For most quantities, a unit is absolutely necessary to communicate values of that physical quantity. For example, conveying to someone a particular length without using some sort of unit is impossible, because a length cannot be described without a reference used to make sense of the value given. But not all quantities require a unit of their own. Using physical laws, units of quantities can be expressed as combinations of units of other quantities. Thus only a small set of units is required. These units are taken as the base units. Other units of derived units. Derived units are a matter of convenience, as they can be expressed in terms of basic units. Which units are considered base units is a matter of choice. The base units of SI are actually not the smallest set possible. Smaller sets have been defined. For example, there are unit sets in which the electric and magnetic field have the same unit. This is based on physical laws that show that electric and magnetic field are actually different manifestations of the same phenomenon. Calculations with units of measurement. Units as dimensions. Any value of a physical quantity is expressed as a comparison to a unit of that quantity. For example, the value of a physical quantity Z is expressed as the product of a unit, Z, and a numerical factor. For example, 2 candlesticks, Z equals 2 candlestick. The multiplication sign is usually left out, just as it is left out between variables in scientific notation of formulas. The conventions used to express quantities is referred to as quantity calculus. In formulas, the unit, Z, can be treated as if it were a specific magnitude of a kind of physical dimension. See dimensional analysis for more on this treatment. Units can only be added or subtracted if they are the same type. However, units can always be multiplied or divided, as George Gamow used to explain. 2 candlesticks times 3 cab drivers equals 6 candlestick cab driver. A distinction should be made between units and standards. A unit is fixed by its definition, and is independent of physical conditions such as temperature. By contrast, a standard is a physical realization of a unit, and realizes that unit only under certain physical conditions. For example, the meter is a unit, while a metal bar is a standard. 1 meter is the same length regardless of temperature, but a metal bar will be exactly 1 meter long only at a certain temperature. There are certain rules that have to be used when dealing with units. Treat units algebraically. Only add like terms. When a unit is divided by itself, the division yields a unitless one. When 2 different units are multiplied, the result is a new unit, referred to by the combination of the units. For instance, in SI, the unit of speed is meters per second. See dimensional analysis. A unit can be multiplied by itself, creating a unit with an exponent. Put simply, units obey the laws of indices. Some units have special names, however these should be treated like their equivalents. For example, 1 Newton is equivalent to 1 kilogram, meter per square second. Thus a quantity may have several unit designations. For example, the unit for surface tension can be referred to as either N per meter or kilogram per square second. Whether these designations are equivalent is disputed amongst metrologists. Expressing a physical value in terms of another unit. Conversion of units involves comparison of different standard physical values, either of a single physical quantity or of a physical quantity and a combination of other physical quantities. Starting with, just replace the original unit with its meaning in terms of the desired unit, e.g., if, then, now and are both numerical values, so just calculate their product, or, which is just mathematically the same thing, multiply z by unity, the product is still z. For example, you have an expression for a physical value z involving the unit feet per second. Find facts relating the original unit to the desired unit. 1 mile equals 5,280 feet and 1 hour equals 3,600 seconds. Next, use the above equations to construct a fraction that has a value of unity and that contains units such that, when it is multiplied with the original physical value, will cancel the original units. Last, multiply the original expression of the physical value by the fraction, called a conversion factor, to obtain the same physical value expressed in terms of a different unit. Note: since valid conversion factors are dimensionless and have a numerical value of 1, multiplying any physical quantity by such a conversion factor does not change that physical quantity. Or as an example, using the metric system, you have a value of fuel economy in the unit liters per 100 kilometers and you want it in terms of the unit microliters per meter. Real-world implications. One example of the importance of agreed units is the failure of the NASA Mars Climate Orbiter, which was accidentally destroyed on a mission to Mars in September 1999 instead of entering orbit due to miscommunications about the value of forces. Different computer programs used different units of measurement. Considerable amounts of effort, time, and money were wasted. On 15 April 1999, Korean Air Cargo Flight 6316 Chinese 6316 from Shanghai to Seoul was lost due to the crew confusing tower instructions and altimeter readings. 3 crew and 5 people on the ground were killed. 37 were injured. In 1983, a Boeing 767 ran out of fuel in mid-flight because of 2 mistakes in figuring the fuel supply of Air Canada's first aircraft to use metric measurements.